Now that we've understood the basic syntax of defining functions, let's expand on this to allow our functions to accept input data. Why would we do this, you might ask? The answer is that inputs allow our functions to be more versatile, more useful, and more reusable. For example, rather than defining a separate function for all possible combinations of values in an addition operator, so having a function for 1 plus 1 and a different function for 1 plus 2, etc., instead we would define the general process of addition and then apply that to any two numbers. So pattern recognition plays an important role here. As programmers, we have to discern what the general process is from many examples. Then we can define a function that solves the general problem, and the inputs provide the specific details. So in this example, we define a simple function called shout, and this function takes its inputs, adds some exclamation marks to it, and prints it to the screen. Now when we call this function, we have to pass in a value for those inputs. So when we call our function, there's a hidden assignment operation that happens that effectively says some text equals the string hello. And then throughout the body of that function, some text has the value hello. The terms for these inputs are parameters and arguments. The terms are often incorrectly used interchangeably. So to distinguish, parameters, which go into the definition of our function, are 0 or more variable names. Okay, these are placed inside the brackets of the function definition, and these are placeholders for the values. That is, until we make a function call, these are just empty variables. Arguments, on the other hand, are placed in the brackets of the function call. These are actual values where we have one argument for each parameter. So the values of our arguments go into each corresponding parameter. Note that the number and the order of those arguments need to match our parameters. So if we have multiple parameters, we need multiple arguments. And in that case, the value of the first argument gets put into the first parameter. The second argument goes to the second parameter, and so on. As a mnemonic, you can consider that parameters are placeholders, and arguments are actual values. If you'd like to refer to these in a generic way, you can just say inputs is a term for either or both. So let's extend our cat example. Copy and paste our code. And we'll call this cat2. Now let's expand this function. So instead of having the default face of two circles in a line, we can actually take in an argument from the user, whoever's calling this function, and have them supply whatever face they want to include in this drawing. To accomplish this, we'll put a parameter between the two parentheses in our function definition. So we'll call this one face. Now this is just a regular variable name. In this case, the name face will get a value when we call our function. So instead of drawing this standard face, we'll replace it with whatever the function's inputs are. So in this case, we'll say plus face. To run this function, we have to make sure we call it. So let's say cat2, and instead of the standard face, we'll pass in, let's say, a happy face. Save our code and run it. So we'll say python functions.py. And notice our cat has a happy face. Let's try some other examples. So we'll say cat2 with whatever you would call this face. And perhaps cat2 with a winky face. So we'll say like that. Save our code and run it. And notice we get 3 cats, each with a different face, all from the same function, just with different inputs. As a useful pro tip, we can actually run the Python interpreter as a sort of mix between its interactive mode and its script mode. To do this, we'll say Python, and instead of just saying our file, we'll say -i, which stands for interactive mode, and then the name of our file, functions.py. Now what this will do is load the script that we've written, functions.py here, into the interpreter, executing it as we've been doing, but then it'll keep the interpreter running with that script loaded so we can continue to use the functions within it. So notice we get our 3 cats, but now we have the 3 chevron prompt, which is asking for more Python code. So I can say cat2, for example, with this face, and we can run that code as well. To exit Python, you can say exit. Note that when I call Python and I provide this -i and the name of my file, these are arguments to the Python interpreter. So the Python interpreter itself is just a program that accepts inputs, runs through some process, in this case executing our code, and returns some result, in this case the result of executing our code. But what happens when we call this function without any argument at all? In this case we get an error. Cat2 is missing one required positional argument, and it tells us the name of the parameter that doesn't have a value. In this case, the variable face has no value, so our code can't execute. Similarly, what happens if we call our function, but we include 2 arguments? Again, we receive an error. This one's slightly different. It says cat2 takes 1 positional argument, but 2 were given. So this demonstrates that the arguments in our function calls need to match the parameters in our function definitions. Let's extend this function again to demonstrate having multiple parameters. So we'll take a copy here, comment out these function calls, and we'll put our code down. So we'll call this one cat3. And now instead of just taking in a face, it'll take in a face and we'll say a tail. Okay. So here's the cat's tail, so let's replace that with our variable. So same way we did it before. In fact, that's the end of it, so that's all we need. And once we've defined it, we can run our function. So we'll say cat3, and we'll pass in some arguments, some values, to go into these 2 parameters. So we'll start with the default face, and we'll say the default tail. Save our code. Back to our command line, and we'll say python functions.py. And it gives us our default cat. Now, if we were to run this with other values, so for example, something like this, I can run our code, and just as expected, we get a different looking cat. But notice importantly, the order of our arguments matches the order of our parameters. So face goes into the variable face, and our tail goes into the variable tail. If I were to reverse this, and run it again, the code still works because syntactically it's still valid, but semantically the result is no longer something that resembles a cat. So this goes to show that the order of our arguments is important, and they need to match the order of our parameters. There needs to be exactly 1 argument for each parameter, and they're assigned in order. Okay, let's try a different function that doesn't involve drawing a cat. So I'm going to comment out these function calls so our output doesn't get filled. Now let's make a function that simulates a coin flip, but rather than just a 50-50 coin flip, let's allow our user to pass in a weight to that coin. So we'll simulate a weighted coin flip. So we could say, for example, coin flip with 90% chance. That'll give us a 90% chance of turning heads. So first off, we're involving some randomness, so we're going to have to import the random library. Normally we do this at the top of the code, but it only affects this function, so let's put it here, as this is a demo script anyways. So we import random. And now we define our function. So we're going to define a function that simulates flipping a coin. So let's call it def coin flip. Now we include our parentheses and our colon to say that this is going to define a function. But we also want to include the ability for our user, or whoever's calling this function, to include the weight of that coin. That's to say the percentage of chance that this coin will turn up heads. So we'll call this variable weight. Now we've already seen how to pull up a random chance through some of our previous examples. So to do that, we generate a random number, r equals random.random. Now normally we've done random.randint between 1 and 100. Here I'm just going to do a random number between 0 and 1. So random.random gives us a random number in this range. So it starts at 0 and it goes up all the way, but not including the value 1. Now, the simplest way to think about how to generate a random chance is to think about a specific example. So we could say if we wanted to create a 50% chance of heads, we would say something along the lines of if r is less than 0.5. Half of the numbers in this range will be less than that point. So this gives us a 50% chance. Now, we don't want a 50% chance. If the user says 0.6, then we want it to be a 60% chance. If they say 0.8, then we want it to be an 80% chance. Now, all of those examples work in the same way. It's just a different size chance, and it's based on our input variable. So we say if r is less than the weight variable. In that case, we'll say that the coin came up heads, so we'll print heads. And if that's not the case, there's only 2 options, so we'll say tails. To try this out, let's call our function. So we'll say coin flip, and we'll try it with a 0.5, so a 50% chance. So this is a standard unweighted coin flip, just to see if it works. So we'll say python functions.py, and it says tails. Run our code again, tails again, we get heads, and then heads. So our outcome here is exactly 50%. We got half heads and half tails, so that seems to be working all right. Let's try a different value. So let's change this to a 0.9. And now when we run our code, it should pretty much always come up heads, with the occasional tails, which does again appear to work. So with this solution in mind, what would happen if our user tried to call coin flip with a different value like coin flip 50 to mean 50%? Instead of assuming that our user knows to say 0.5 to mean 50%, what happens if they say 50 to mean 50%? Well, in this case, this would equal 5,000%, which would give us effectively a 100% chance of generating a heads from our coin flip. So that seems wrong. Let's see if that's true. Code runs. Now we're getting 2 flips each time because we didn't comment out our previous run. So let's comment that out and try again. And note, we're pretty much only getting heads. Not pretty much only getting heads, we are exclusively only getting heads, because again, a 5,000% chance of flipping heads effectively means a 100% chance of heads. Okay, and what would happen if our user, instead of saying coin flip 50, said coin flip of the word 50, or even 50%? In this case, when we run our code, it crashes. There's a type error. The comparison operator less than is not supported between instances of a float and a string. And that happened on line 37 at this comparison. So we go to our code at line 37, we see r is less than weight. So our weight variable here, which we passed in as the words 50%, is a string. And on the left, we have a float from our random number generator, which gives us float is less than string, which is an error. So recall that Python is dynamically typed. This means variables, including parameters, can have any kind of data type. This is as opposed to statically typed languages like Java, where you have to declare a specific type for each variable. So you'd have to say int x equals 5 instead of just x equals 5, or string y equals hello instead of just y equals hello. Now, the advantage of a dynamically typed language is that it allows flexibility in our code. Sometimes it makes sense to reuse our variables for different types. So, for example, taking user input, which happens as a string, and then converting it to an int. Since we don't need 2 different versions of the same user input, we can just use one variable and have it store multiple different types. Similarly, having dynamically typed variables means that we can make a function that seamlessly handles multiple types of inputs and just treats them differently. The disadvantage is that we now have the freedom to make some serious mistakes. In statically typed languages, the compiler can point out our errors. So if we pass in the wrong type of value to a function, it can say, that's not the right type for this function, and it will crash at compile time. In dynamically typed languages, however, the compiler can't check for data type mistakes. So instead, they crash the program at runtime. The solution is to either always use our functions correctly, or to check the types of our inputs inside of the function. So let's expand this coin flip function with type checking to allow the user to call with either coin flip 50 or coin flip 0.5, so either with a floating point number or an integer number. The idea is we'll distinguish between integers and floats in our argument. So if it's a float, we'll treat it as though it's a weight between 0 and 1. If it's an integer, we'll treat it as though it's a weight between 0 and 100. If it's something else like a string, then we'll make sure our code handles that gracefully without crashing. We'll also need to check for bad values, so those are the values outside of our expected ranges. We've already learned how to determine what the type of a given value or variable is in Python. We can use the type function. Just to demonstrate that, I can open up Python here. I can say the type of the value 3, and that's an int. I can say the type of 3.14, and that's a float. I can say the type of hello, and that's a string. So this function takes in an input, whatever value we want to check, and it returns the type of that value. Next, let's use this information so we can expand our coin flip function to allow type checking. This will mean the user can call our function with either an integer, such as 50 to mean 50%, or with a floating point number, such as 0.5 to mean 50%. The idea is to distinguish between integers and floats as our arguments. If it's a floating point number, we'll treat it as though it's a weight between the numbers 0 and 1. If it's an integer, we'll treat it as a weight between 0 and 100. If it's any other type, like a string for example, then we'll just exit gracefully. We'll also need to check for bad values to ensure that our argument is within the correct range given either type. So returning to our function, let's just expand this design in comments before we start coding. So far what we have is to flip a coin based on whatever weight that we're given. But before then, what we're going to need to do is, first off, check the parameters type. We have two types that we're interested in this code. So the first is an integer and the second is a float. In the case of an integer, we'll have to verify our values to be within the correct range. So that's going to be, for an integer, between 0 and 100. And then we'll want to flip a coin. If it's a floating point number, we'll still need to verify our values, but to a different range, in this case between 0 and 1. And then we'll want to flip a coin, which we're already doing, so we have all of this code here. Notice if it's a different type, we'll just simply ignore it. So first off, let's check if our input is an integer. So we'll say if the type of our parameter weight is equal to int, then we'll handle it as an integer. So to do that, we first have to verify its value. So we'll say if 0 is less than or equal to weight, and weight is less than or equal to 100. So now weight is going to be a value between 0 and 100 if we get into this point here. And in that case, we will flip a coin. So we've already seen how to do this with integers, so we'll generate another random number. So r equals random dot randint between 1 and 100. So note that this is in the range from 1 to 100 inclusive, a little bit different than how our other random function works. And we'll say if r is less than or equal to our weight. Note we have equality here just because when we're using randint, it includes that last value. So think in terms of our edge cases, if the user passes in a weight of 100, meaning they want a guaranteed chance to roll a heads, if our random number here was generated as 100 as well, then that should still be a heads. So that should still make this if statement true, in which case 100 being less than or equal to 100 would be true, but 100 being less than 100 would be false. So in this case, because our random generator includes its last value, we'll use less than or equal to. So if r is less than the weight that we passed in, then we will say success. So in this case, we'll call that heads, and in all other cases, tails. Now we need to do a similar sort of operation for the floating point numbers. So we could say if the type of our parameter weight here is float, then we'll verify the values and flip a coin. So to verify the values, we want to know, is weight greater than 0? And is it less than or equal to 1.0, our upper bound? So it's a floating point number in the range 0 to 1. And in that case, we will flip a coin. So we'll take all this and push it into that if statement. So let's save our code and try it out. So we have 3 runs here already. Now what we're expecting in these is this one should be mostly heads. If we change this one, let's make it so that it comes up more obviously as one or the other. So this should be mostly tails. And in this case, we're not handling the string at all, so this should do nothing. Now recall previously it crashed, so doing nothing would be an improvement. Save our code, and let's try it out. So we'll say python functions.py, and we get heads and a tails. That's what we're expecting to see. If we run this many times, we should see that pretty much every time. Not every single time, mind you, because there is still some randomness, but for most of our cases, we see heads and then tails. Notice we had 3 coin flips running in our code, or 3 calls to this function. The one that passed in a string, however, if we look through our code, string is not of type int, it is not of type float, and then nothing else is in our code. So if it doesn't match either of those cases, then just nothing happens. So looking at our code, this is not written in the cleanest way possible, so let's see if we can't clean it up a little bit. Noting specifically we are flipping a coin in 2 separate places, which is more or less the same basic operation. We can certainly make it so that it will work in one place. So a simple way to clean up this code would be if we have an integer, let's convert it into the equivalent floating point number. So if we're given a 50, we'll convert it to 0.5. If we're given 10, we'll make it 0.1. If we're given 1, we'll make it 0.01. Which is to say we'll take that integer and we'll divide by 100. So we'll say if we have an int, then weight divide equals 100.0. Note we could have said something like weight equals the float of weight divided by 100, but this accomplishes the same thing with fewer characters. Note, because we're using division and because there's a floating point value in the inputs to our operation, the result of this operation will be that weight is now a floating point number, and it will be divided by 100 from what it was originally. So if our user passed in the value 50, at this point the weight will be 0.5. Now if the user passed in a value outside of our range, let's say 500, then this would be a floating point value outside of our range as well. So we still need to check the range of that. Now what we don't need is all of this code here. We'll say int2 float. So we check the parameter's type. If it's an integer, we convert it to a float. Now the next question says, if it's a float, which is either because that's what was passed in, or because we've converted it and gotten here, in either case, we still need to check that the value is of the correct range. So we'll say all of this to verify our range, and if that's the case, then we'll flip our coin. Notice still if we're passed in a string, that won't match any of our branches, so nothing should happen. Let's save our code and try it out. Running our code, we get heads, tails, and nothing for the third branch, so strings are being handled correctly. Heads and tails is what we're expecting, because again, remember we're calling it with 90% and 5% chance. So if we run it multiple times, we more or less get the same answer for the vast majority of executions. Let's try out some other tests to make sure that our code works. So let's, for example, put in a 900% chance, or a negative 0.5% chance. And now in these cases, all of our inputs are invalid inputs, so we get no outputs.